I'm going to make you sit where we can all recognize you in just a minute. So welcome, ladies and gentlemen, to the inaugural Christopher S. Peebles Lecture on Information Technology. I'm Craig Stewart, Executive Director of the Pervasive Technology Institute and Associate Dean for Research Technologies at Indiana University. I have the pleasure of introducing the Peebles Lecture Series, and then after that, Professor Andrew Lumsdaine of the School of Informatics and PTI will introduce our speaker. Christopher S. Peebles came to Indiana University in 1985, has spent more than 23 years as the director of the Glenn A. Black Laboratory of Archaeology. I've heard him tell me that his dissertation was information theory in the guise of archaeology, but he spends a lot of time digging in the dirt for a guy who thinks he's an information specialist. Chris became a member of what was then called the Bloomington Campus Computer User Committee early on in his time at IU. And shortly after that, he was recruited by Polly McClure to become part of the information technology organization here. Chris has held a number of leadership roles over the years in IT. He's been Dean of Information Technology and Associate Vice President for Research and Academic Computing for more than a decade during the course of his career at IU. I note that Chris was succeeded by Brad Wheeler, who's now Vice President for IT, and I now sit in the position that was so ably held by Chris for a decade. Chris was twice the interim CIO of Indiana University. As a leader in information technology, Chris imbued the university computing services and later university information technology services with a sense of dedication and commitment to the scholarly activities of students, staff, and faculty. It was Chris who led IU early on in the systematic analysis of user-perceived quality of our services, and with Lori Antolovic, implemented activity-based costing, analyzing the true cost of all our services. As a result, we know what our services are, how much they cost, and how people like them. We're almost unique among universities in the U.S. in having that information. That allows us to make fact-based decisions to better improve our services and better serve the university. Chris is a researcher of the first rate, a person dedicated to scholarship and education. When Chris retired as Associate Vice President, then Vice President McRobbie started up the Peebles Lecture Fund at the IU Foundation. Please join me in acknowledging the many people who are with us today, and if you wish to stand, you may, those who have donated to the endowment fund to endow this lecture series. Incidentally, President McRobbie and Vice President Wheeler are both in that category. Both are on travel. Send their warm regards and congratulations. It's an honor to have Chris with us in the audience. Chris has been a mentor of mine for more than 2 decades. I owe him a particularly deep debt of gratitude. The entire university is indebted to Chris, and let me ask you to join me in thanking Chris. Chris, would you please stand? It's been a good couple weeks at IU. Last week we dedicated the IU Data Center. This week we dedicated the IU Innovation Center, the building that we're sitting in now. Last week, President McRobbie bestowed upon Chris the Thomas Hart Benton Mural Medallion, one of 3 medals that's awarded by the university. This medal recognizes individuals who are shining examples of the values of IU and the universal academic community. And we follow that up this week with the inaugural Peebles Lecture Series. So with thanks to Chris, thanks to all who donated to the Peebles Lecture Fund, thanks to all here in attendance and all watching us over the web, let me hand the podium over to Professor Andrew Lumsdaine, Professor of Computing in the School of Informatics and Computing, also a leader of the Pervasive Technology Institute and a director of the Open Systems Lab. Andrew.
So it's my distinct pleasure to introduce Tom Sterling, Professor Sterling, to give this inaugural speech. I've known Tom since, give away too much to say how many years, but since I was at Notre Dame and we were both working on the HTMT project. Professor Sterling received his PhD in electrical engineering and computer science at MIT in 1984, where he was a Hertz Fellow at the time. Since then, he's been one of the real driving forces in high-performance computing, both in terms of hardware, architecture, and systems software. Thomas is perhaps most well known in general computing circles for his contributions to cluster computing. And I think it would be a fair statement to say that he actually invented cluster computing. He christened his first cluster, this is a term most people may have heard, Beowulf. And that terminology sort of took on a life of its own, becoming a common term for cluster computing and even becoming a slashdot meme. People may have heard the term, imagine a Beowulf of these. But for his leadership in cluster computing, Professor Sterling was recognized in 1997 with a Gordon Bell Prize. Professor Sterling has really been at the very leading edge of high-performance computing, and I think as people may have seen in my comments in the flyer that was circulated for this talk, I feel he's been defining that edge. While the rest of us were worrying about teraflops, Thomas was already worrying about petaflops and designing machines to compute at that level. Now that the rest of us have caught up and are worrying about petaflops, Thomas is worrying about exascale. And exascale is a change in two ways, an advance in two ways from petaflops. I mean, first, we're advancing, of course, from peta to exa in terms of size, but I think more importantly, the emphasis has been changing from flops to scale, indicating or really recognizing the fact that the problems now that we'll be solving on these next generation of machines go beyond the traditional scientific computing, PDEs and ODEs and so forth, and will be including network types problems, social networks, bioinformatics, complex systems, and so forth. So Professor Sterling is currently the Arno and Edwards Professor at LSU in the Department of Computer Science and a faculty member in the Center for Computation and Technology. He's a faculty associate still at Caltech, California Institute of Technology, and a member or a visiting distinguished scientist at Oak Ridge National Lab. And there was one I didn't get from his website. He's currently a CSRI fellow at Sandia National Lab. So Professor Sterling will now give us his presentation, HPC and Phase Change towards a new parallel execution model. And I promise that this will be one of the best talks that you will ever hear about high-performance computing, and probably one of the best talks that you will ever hear about anything.
Obviously, no pressure. I have to say thanks in any number of ways. First, I want to thank Craig and Andrew for inviting me to Bloomington, University of Illinois. This is my first visit. I also want to thank Indiana University for the, and I can say this without concern of being caught incorrect, an unprecedented honor to be the first of a new lecture series for Chris Peebles, and I hope that I can begin to do it justice. But I was expanding on the theme of this and thinking, in a mere 100 years from now, they will celebrate the century anniversary of the Chris Peebles Award, and they will look at this videotape. Of course, I trust it will then be digitized in a way that I will be a true three-dimensional hologram, somewhat younger, and maybe more expansive in nature. But it's a wonderful opportunity for me. So thank you all very much. I am pleased, therefore, to discuss over the next few minutes an important and dramatic change that we are now as a community, and that's the high-performance computing community, more generally computing in general, experiencing right now. And so my theme is to discuss that change, to discuss its implications and the form that it might take, and how we as a community must rise to address that, and to suggest, perhaps humbly, some of the directions based on the work that I and my colleagues have taken over the last few years. You know, it's interesting. I promised Andrew that I wouldn't talk about Beowulf clusters, and I don't have a single slide that refers to them. But the occasion of the emergence of clusters along with massively parallel processors and the use of what was then referred to as the killer micro was approaching 2 decades ago. And of course, these histories never have sharp turns. They're long tails. And it was about 2 decades ago that the last time that the community embraced a new paradigm for the design, control, and application of high-end computing. And it has been since then that we have leveraged that model, that phase of high-end computing, and that we're now, only now, in the last 2 to 3 years, entering the next and possibly the last phase in high-end computing as we know it. So there are basically 3 topics that I would like to address to you. First is this idea of a phase change, give it a little bit more a depth of understanding. And then I would like to underline, highlight a key aspect of what we mean by phase change in computing, and that is the idea of a model of computation, of an execution model, the paradigm by which all of the computing systems are derived, devised, controlled, and applied. And then to get a little bit more specific, I would like to talk about one experimental model, a model called ParalleX, that I and colleagues in various institutions have been working on. Not a tool that we expect everyone to embrace and employ, but rather an experimental vehicle that allows us to test some new ideas and to employ them with respect to applications to derive greater understanding of the possible future. And I'll close in the last few slides by giving you some early inchoate results of some experiments that we've performed that, if not definitive in their finality of correctness, at least it proves to be encouraging, maybe even a little exciting. So let's first talk about the idea of a phase change. You know, we've been on this piece of the S-curve of high-performance computing so long that we forget that the S-curve turns twice. We have, when microprocessors were literally toys for the insides of games and terminals and simple PCs, we were building large multi-million-dollar vector computers and SIMD machines. At some point, at a critical moment, the capability of these microprocessors, the cost of them, and a number of other attributes, including available software, came together almost spontaneously and created a new opportunity. And that opportunity proved to be the combination of massively parallel processors and clusters. You have here at Indiana University one of the fathers of that field, Geoffrey Fox, who led the way for many of the rest of us, and was certainly a driver and motivator for my own work in those early years. Now, why, in fact, does the field change? Why can't we just build better and more powerful machines as the technology arises? Why can't we do the same thing we did before? The answer is because as the technology does shift, different attributes of that technology shift at different rates. It's also because certain techniques that we use that are cost-effective at one point prove not to be cost-effective or fail to scale, fail to grow the number of orders of magnitude that the technology enabled. Underlying computing, so I've been accused of being the person who finds the cloud in front of every silver lining. When I think of performance, I think of what goes wrong, not what goes right. And I'm going to introduce here 4 principal factors that degrade performance against the optimal. I call them slow. Right? Starvation, latency, overhead, and possibly slightly arbitrary weighting for contention. Contention gave me slock, and that just didn't have the impact. So waiting for contention. And in fact, that's right. Starvation is the insufficiency of parallelism, of concurrency of work, either totally for an application or there may be enough work, but it's not adequately distributed. It's not load balanced. Latency is the delay incurred by having to wait to cover some distance, either for access to some sort of information or for some remote service requested. Overhead, this is critical, is the amount of additional work that you wouldn't have done if it was a sequential execution, but you had to do to manage the parallelism. And finally, contention. Well, contention, of course, is the delay incurred by waiting for a shared resource for other agents or entities to be done with it so that it can become available. These four factors combined to be the principal drivers that technologies and architectures have to address. And they change depending on the technologies. In particular, but not limited to, the issue of starvation, the amount of concurrency. That's the topic I will talk about at length. Other factors come into play, other nonlinear constraints. One that we will discuss will be power. One we will not discuss will be reliability, but equally important. If the machine doesn't run, then the rest doesn't matter. A paradigm shift requires us to change the organization of computing, change the architecture of the system, the structures by which the technology is applied through its logic, change the model by which we program, we bring our application to bear to the problem, change the software that enables the exploitation of the hardware, the operating system, and more recently, the runtime system that bridges the gap dynamically between the application programming language compilers and the underlying hardware system. I suggest that we are now actively entering into the sixth phase in computing. Your history may be different, but allow me at least to justify that. When I was as young as some of the faces I see here, computing was easy. We would pick up the textbook and it would teach us fetch, execute, write back. That was good, and then we would fetch again. And that was the first paradigm. It was pretty close to how von Neumann described it in the mid to late 1940s. And it was used when computing technology was incredibly expensive, when an ALU would be big. When a bit of an ALU would be big. Chris and I were talking about old machines we have known, and we didn't say it, but loved. And I was describing a computer I fixed back in, I won't tell you which decade, and it was a single bit of the accumulator was this big. I fixed it by removing the 3-pin integrated circuit and replacing it with another 3-pin integrated circuit. Some may remember that was called the transistor. By the late 1960s, the technology was fast enough. We could build it dense enough so that we were wasting time if we didn't find ways to overlap the instruction execution. And so sequential, I call it the sequential instruction issue phase era. The instructions would still be issued sequentially, but they would be overlapped. And that continues right to this day. Pipelined execution, reservation stations, Tomasulo algorithm, instruction level parallelism, and so on, including some speculative execution. By the mid-1970s, the technology advanced and allowed us to again build denser structures, and Seymour Cray, among others, led the direction to vector computing. Vectors were beautiful, elegant, lovely, and if you wanted to do dense matrices, dense vectors, and you didn't want to scale beyond what they could scale to, this was clean in the way that we hunger for clean now. We don't have it. But vectors didn't scale, and so an added layer, we now call a PVP, or parallel vector processing, was used up through the alphabet soup machines, the XMP, YMP, C90, T90. Further attempts, new companies that tried with CCC, the Cray 3 and the Cray 4 were not commercial successes because the technology kept moving forward. giving us SIMD computation, where now we could, if the cores were small, we could build lots of small cores, but the distances across the machine and the clock rates were such that we could effectively broadcast an instruction to all of them. We can't do that today. SIMD machines provided us with better performance to cost than we had had through any other means. And then, again, by the beginning of the 1990s, the work of Jeffrey and his colleagues, and a little bit later work with myself and Don Becker and the Berkeley folks and others provided a natural medium by which communicating sequential processes, named, I believe, by Tony Hoare as early as the mid-1970s, became the medium of choice, and still in the scientific computing world is the dominant model using the community formalism of MPI. Now, I walk you through this because I want to give you as an example this constant history moving forward as the technology moved forward and enabled new capabilities. Those capabilities were only revealed through the medium of architecture changes, those changes in structure requiring changes in programming methods and models, which means different models of computation. Each of these phases has their own model of computation. Recently, the Defense Advanced Research Projects Agency has sponsored several new, fairly expensive and in-depth projects. I'd like to spend a couple of minutes and show you some results from one of those. This is the DARPA Exascale Technology Project. It was led from Indiana by Peter Kogi at University of Notre Dame, and the slides I show you, I hope I've given credit to Peter, came directly from his spreadsheet. The question was, how will we achieve exascale computing by the end of the next decade? Where does that question come from? I have too much self-pride to throw up yet another top 500 chart, so I'm not going to do this. But if you were to extrapolate the top 500, that's the number one machine measured by that all-important benchmark LINPACK. If you want to run infinite dense matrix, the nice thing about LINPACK is it will ultimately die. The HPL benchmark will die because in order to compute Rmax, you will be required to do so much computation that I predict the computer will not stay up long enough to finish the benchmark. This might be a fitting end to a benchmark. Actually, I'm a big fan of being able to measure things, and we certainly now have a long baseline. This study, which involved many of the best experts in this country, and I was honored to be among those, among the participants, not the experts. Okay, that was awkward. I don't usually brag about being an expert, but I am an expert about myself and my own expertise. So I guess I'm qualified to do that. Let's pretend that last 30 you can delete that, right? A number of different design points were studied in depth to appreciate how they would scale up. And so here are three transparency. Here's one that just simply shows us the gigaflops with respect to time. And it is a surprising factor that line that says exascale is where we want to be. The top 500 list projects that by September 16th, 2019, and I've forgotten what time, it depends on the time zone anyway, that we will hit an exascale. Well, in fact, expanding on the various kinds of design points, from conventional heavyweight processors like x86 machines, alternatively looking at such powerhouses like the Tyrannosaurus Rex power series of architectures out of IBM, versus lightweight cores such as ARM and other embedded processors. And the message came out very clear. The conventional processors won't make it. Now, there were constraints, I don't have time to discuss them, of power and other issues. I'll show you power in a moment, that bounded the space. You say, well, why can't I just take your 33,000 square feet of floor space and build myself an exaflops computer? It would take more than those generators to power it, I assure you. So one of the most sobering results from this is almost no approach that we understand at this time will get us to an exascale in the time that seemed to be natural expansion. If we look at the power efficiency, where what we want is something on the order of 50 gigaflops per watt. 50 gigaflops per watt. That's extraordinary. Again, we find that almost no method will let us do that. A simplistic-minded view that we could derive would do so. The best, I'll give you the bottom line, power numbers that have been studied through this and other approaches suggest that the power required without revolutionary changes in architecture would be something like 120 megawatts plus or minus 50%. The most optimistic numbers I've seen are just under 70, that's 70 megawatt, and the threshold of pain where it is practical is assumed to be between 20 and 25 megawatts. A consequence of this study, if you were to take it face value, is that we can't get there from here, at least not in that time frame. And you know, there's not a lot of headroom, because by then we will be at 10 or 11 nanometers. And any of those who go around measuring the distance between atoms knows that we don't have a lot more room to squeeze out of that, and other little problems like quantum noise come up. Let me show you one other problem, and this is the one I want to talk about, and that is concurrency, parallelism. If we expect to perform at exascale, and yes, the term exascale is used to recognize, first, that there are many different dimensions we want to expand upon, and secondly, that exaflops is not the number we're looking for. Sustained exaflops would be potentially impossible. Here, you see, again, struggling with several design points, the effort to try to get enough concurrency based on assumed clock rates. You need not just billion-way parallelism, but more like 10 billion-way parallelism. Where are we today? Nominally a million-way parallelism. So we are looking at probably, and that's the biggest machines. That's a blue gene machine with the largest number of cores, and each of the cores running several instruction-level parallelism. We, at the moment, don't know how to get there. And much of my talk is going to be how to get us closer. So, no, I won't read every bullet point here. Quickly scan, but let me highlight a couple of points. If we were to extract from that study, from the second study run by Vivek Sarkar on exascale software, from a study that I have the opportunity to be part of, the National Science Foundation's exascale point design study, from the work coming from some of the DOE workshops as well, we have a sense of at least one possible place we would be. I already said that the feature sizes are likely to be between 22 and 11 nanometers. Let me just say that if I were wearing an Intel hat, I would be telling you, no, we're going to be there at 8 nanometers in the same time frame. Energy requirements, for total average energy per floating point operation, that means not just the operation itself, but the data movement and control probably required, on the order of 25 picojoules per floating point operation. I've already referred to the 10 billion way parallelism due to clock rates and other constraints and instruction level parallelism. This is several 100 million cores. Those cores may be of different characteristics. We're anticipating heterogeneous architectures. The clock rates may not, even in the next 10 years, increase dramatically. In fact, we even find with IBM, we find that the power series architectures, which hit 5 gigahertz, is planned to actually go down again into the area between 3 and 4. And Ravi Armilio of IBM at Austin has been very aggressive in pushing this, some brilliant engineering, but even there it's unlikely that that will be able to be continued. Jumping around, we see things that we expect, a mix of optical communication and wired communication. We see packaging of dies, multiple dies simultaneously, one on top of the other, with via, I hate this, communicating via vias, in English language, I know it's Latin, going through, and not just worrying about along the edges. How do we cool the interior of that? A question that's not yet understood fully. We see the use of yet higher levels of memory capacity and memory hierarchy, new emerging non-volatile memories, such as phase change memories, NAND memories, and MRAM. All of these showing some kind of promise, but with very different operational characteristics and constraints. All of these together suggest the class of machines that we're confronting, unprecedented in so many dimensions that whatever we think we know does not apply even 10 years from now. If I have asserted that in order to address the challenges of new computer architectures spurred and necessitated by new technologies, that a model of computation, an underlying foundational model, has in each case come to play so that we could build methods to both control and program these machines, then we naturally must ask the question, if we're in a phase change, if this is the sixth phase change, what's the new model of computation? What is the execution model? What does it need to do to make it possible to achieve exascale computing? And are there any ideas, any concepts that allow us to go forward with this problem? Here's a cartoon that, when you want to do the system stack, it's sobering to recognize that it quickly stops being a stack, because we know, those of us who work practically in this field know, that there is no single programming model, no one language that's going to fit all. And we can anticipate, if the past is a precursor to the future, that there is not going to be a single architecture, but rather families of architectures. Different balances for different cost operating points, frankly, just for different size, weight, and power issues. We know that some of the software will tend to be common across these systems. Others will be distinct. We know that some of the software will be leveraged from the past in order to enable seamless transition to the future, while others will be innovative and unique to get the best possible behavior out of these systems. And so this diagram, shaped as an hourglass, suggests, first of all, that supercomputing is about time, and that in order to achieve the best possible time, all of these layers have to work together in an integrated, synergistic fashion. At the bottleneck there, I've put model of computation. The intent was to suggest that all of these are governed by, influenced by, and contribute to the model of computation, but I made a deep mistake here. And I even tried to fix it last night, but I found out that A, I didn't draw this drawing, and B, it's in a piece of software that I don't have. And all I wanted to do was rotate it, and I could probably do that with this, but that won't change what's on there. So you're just going to have to accept that, in fact, it should be vertical. It should be a cut set through the entire layer. Because ultimately, what happens? An operation occurs on some data at some place in your machine at some time. How did that happen? Well, there was a decision chain. Whether you intended or not, there was a chain of events, decisions that were made at every level, including the arbitration network in your bus and something in some other chip that you never think about. Your compiler did something by mistake. Your programmer may have done something. Everything influenced that event. Well, if that's the case, wouldn't it be nice if we actually intentionally controlled that event? Because after all, that's what performance optimization is about. And so that decision chain is, in fact, a consequence of the model of computation. And so it's that model that we want to talk about. So what is the purpose of model? Well, it is not an academic intellectual exercise. This isn't job security for aging professors. Right? This isn't yet a new way to get papers published. In fact, let me tell you, the young people, this is not a way to get papers published. If you want to get a paper rejected, write it on what I'm about to tell you. 5 years from now, it won't be accepted either because it'll already be old hat. This happened when I did Beowulf. I kept submitting papers on Beowulf. Can't happen, won't work, won't be done. Technology's not there, the methods aren't there, won't happen. Then I submitted a proposal and I got something that's already been done. Everyone knows this. There's nothing new. So, wasn't there supposed to be, a honeymoon period? When do I get Beowulf published? Well, never happened. Okay, it did happen. But I ended up writing books. That way, MPI Press. a model of computation is, in fact, a critical tool for realizing the effectiveness of new scales of applications with new classes of machines. As I have said, they're there to address the challenges of the new technologies, even as they expose and elevate the opportunities that the new technologies imply. They do reflect the change in the paradigm or the phase of our field. They always have, and I'm suggesting they will continue to do so. But a model of computation is more useful than that. It's not simply a cult or a religion. I'm a communicating sequential processes person. Yes, no, I'm a vector person. Although that has happened. It is, in fact, a means of co-design of all of the elements that go into a system. It's almost a reduction in complexity. If you wanted to design everything, you'd want to design each piece with respect to everything else. That's an order n squared problem. Right? If you accept for a moment that the correct model of computation is handed down to you, then all you have to do is design each piece with respect to that model. Hence, you have an order n rather than order n squared. Okay, it's order n plus some constant, but let's not talk about that. A new model of computation embodies and lets you exploit and support new methods that old models of computation preclude you from using, actually provide barriers. The term deadly embrace has been used frequently to talk about the limitations of conventional practices. And so new models of computation move us forward. An execution model has a number of different attributes. This is a hard thing to kind of convey. I'm only going to touch on the top-level notions and leave for another time the greater details. First, it is the representation of the system in its total sense. I gave a talk at a HPC user forum in Stuttgart a few weeks ago, and the title was "The Execution Model is the System." The execution model embodies the strategies. As I said, to solve the problems that the technologies and architectures impose, even as they allow you to exploit and reveal the new capabilities that the technologies enable. An execution model does, in fact, reflect and incorporate the semantics of the names of the entities which are manipulated, the kinds of actions and their organization that can be performed, in our case, the forms of parallelism that can be exploited, and this is all too critical to achieving the scalability that we need in order to get to exascale. They have very practical concerns as well. On one hand, they need to allow you to control the hardware, to manage the power consumption in the future, and potentially reconfigure the system in the presence of faults for graceful degradation. You don't actually ever want to fix a machine in the future, right? You want to build them one, package them, and that's it. Close them up, put them on the floor, and let them just slowly decay. I predict that there's going to be a class of machines, we're going to call them depleted computers. You heard it here first. Depleted computers. They're just going to get down to and I'm showing my electrical engineering bias, the half power point. I don't mean watts. I mean they'll only be capable of performing at half the power. And then Craig and his colleagues will move it out of the floor, because by then you'll be ready to have a 4 times the performance machine that the first one was in the same floor space and power. And then you'll sell it to somebody in South America or Africa or penguins in Antarctica or wherever else where they could use the heat. And this will give us the highest availability. Okay, so these are things that you need the execution model to be able to do explicitly. Here's the irony. There are also things that the execution model will not do explicitly. It will specify policies, invariants of operation that you have to be guaranteed will occur, but you do not specify how they are to be done. This is absolutely critical for the flexibility of a model of computation. If you were to specify everything, you would be too constraining, too restrictive, and you're only a narrow class of machines. This allows wide variation in terms of their implementation in hardware and software. Once you've achieved that, then you can talk about devising the abstraction of the computation with respect to the physical relationships of the machine itself. I propose in the future you're not going to want that to be nailed, as we do mostly today, but rather to, and I use a metaphor, hover above and be able to drift across the system as the system degrades, as you change the configuration of the system, possibly for better power management and for load balancing. You do all of this in part because you want to achieve a kind of commonality, a commonality that will provide portability across different machines at any point in time, across different scales of any given machine, and across different generations of machines that are governed by this kind of model of computation. These are the attributes of an execution model that you need to incorporate when you're proposing such a model. Well, assuming that's what we want in terms of a model, what in fact do we need for exascale? Well, we need a discipline that provides the governing principles that guide the realization, implementation, and usage of these future systems. Among the things that we are most concerned about is the ability to mitigate the implications of latency. It's a combination of hiding latency effectively, as well as managing locality so that we won't experience it. And ordinarily in this field, we'd be talking about time. But we're also talking about power. And to move data is to use power. So our cost function is more complex than it had been. We need a model that will exploit 10,000 times the parallelism that we're able to use today through a number of different techniques. Part of that is that we need fine-grained synchronization. Synchronization methods that have such low overhead that the granularity of the parallels actions that we exploit will be much smaller, and usually, but not always, that implies a greater amount of concurrency and therefore the ability to scale up. We know that we cannot know at compile time all the things that are going to happen and they're at runtime, and therefore we must use runtime information. This means systems must be runtime adaptive, and a new model of computation must support that. In addition, we have to be able to deal with the presence of faults. You say, what's the problem? Well, get that envelope we all write in the back of, and just do the math. Figure out what the MTBF, the mean time between failure, will be for a single point failure mode. Find out what it's going to take to checkpoint the full memory system. And guess what? MTBF is less than checkpointing time. So you will have, at the exascale, you will have your system breaking before it can save the content of the memory in order to recover from when the system is going to break. This is an infinitely recursive problem. You can't win this game. So we have to have new methods of dealing with that. And finally, we have the challenge of complexity of design. And we need a new model of computation that allows us not to be forced to try to mimic this notion of sequential instruction issue, this sequentiality, sequential consistency. I remember being an advisor to MCC so many years ago. I was advising their parallel processing group. They had all these different machine designs. They named one Rice Krispies and one Cocoa Puffs, and there was one, I've forgotten the other one, and I just had problems. And I told them I had problems with them naming these parallel machines after cereals. Well, but we do that ourselves. We are constantly saying, I want to build a parallel computer, but I want it to look like a serial machine. Get over it. It's the third millennium. Move on. So let's see how we might move on. I want to motivate this. This is an old, the results of an old experiment that was performed during the DARPA HPCS program, specifically the Cascade project. I and my colleagues, I was then at Caltech, and at the Jet Propulsion Laboratory, did this. And I'm sorry, too many dots. Let me just explain what you're supposed to get from this. And this is when I wish I had a laser pointer, but work with me here. Each of the ensemble groups is the amount of parallelism. This is a comparative analysis done through simulation. It's a parametric study. It has the value of being unrelated to anything in the real world, so you don't have to worry your silly little minds about whether this actually means anything. The comparison is between a machine that sends messages and causes work to happen at remote places according to the message versus conventional machines that simply send messages back and forth and wait for a response. The horizontal axis is system average latency time. Each of the different ensembles is the amount of average parallelism per node in the system. All the other little colored dots there represent the different ratios of local and remote accesses. And the story is pretty clear. So this is a comparative study. So up is good. And what we find is if you look at your right, where the parallelism is very low, you see that, in fact, during some part of the parametric study, you see that you actually get negative results. This is bad. It claims, therefore, that the old-fashioned way is the good way, and in that regime of computing, this is true. But if you look towards the left, as the average parallelism grows, and not by orders of magnitude, or not more than 1 or 2 orders of magnitude, you see that there are areas of possible performance benefit, switching to a message-driven approach versus a message-passing approach that span between 1 and 2 orders of magnitude. Nothing else has changed. The technology is the same. The number of nodes in the architecture is the same number of threads. The workload is the same. The characteristics of the workload is the same. The only thing that has changed is the stratagem, dare I say, the execution model, by which the computation is performed. And this chart motivates the next few graphs, which is suggesting that we consider an old idea using message-driven computation versus message-passing computation. Message-driven computation is at the heart of the experimental execution model ParalleX, a model that incorporates different domains of locality, of synchronous operation, and across all of these does so with a kind of a global address space, not a cache-coherent address space, as you might hope for from Silicon Graphics, not a truly limited and restricted address space that you might get from partitioned global address space systems as Titanium and UPC, but something in between. It is an execution model that instead of running a particular process on a particular node and waiting for remote actions, simply works as a work queue model, does the work it can do locally, and when it can't do any more work locally, sends the work away to wherever it has to go, and immediately takes the next piece of waiting work to be performed. An obvious and simple idea that we nonetheless don't use today. It does this through a combination of message-driven computation, messages that tell us not just about the data that we want to operate on, but the work we want to perform on that data, and at the same time, a variation on yet another old idea, multi-threaded computation. The ParalleX model has this nasty habit of wanting to name everything, almost everything. It doesn't name parcels, but it names everything else, including the threads, and including these large processes, no longer the process that sits on the processor that you would get statically in a model of, in the CSP model of computation, but rather a namespace that allows you to span multiple nodes, many different pieces of data, and I'll show you a picture in a moment. And finally, we coordinate this with a lightweight synchronization object, what we call LCO, for a local control object, of a number of different semantic characteristics that remove the global barriers and allow a freer overlap of different phases of computation. And I want to just spend a couple of minutes showing you some of the details of this. I will not go into complete detail on all of this. Now, if this were a mere 20 years ago, and I had the honor to be giving this talk 20 years ago, I would have put up this drawing. This is a conventional communicating sequential processes, sometimes referred to as message passing diagram. And here you have a process on each processor, and those processors send messages back and forth to each of the processes, and they share some global synchronization, a global barrier. If we look at the ParalleX model, we get something like this. Well, the little squiggly worm-like things are threads. These are not static threads, all of which do the same thing. These are dynamic, ephemeral threads that may do very different things, those little squiggly lines. But you'll notice that the processes are not limited to a single node or locality. They can span multiple nodes. In one case, between A and B, you see that they even share a node. A process today, as well as in the future, is in fact not an action, though we attribute action to it. It is in fact a context, a namespace in a hierarchy of namespaces. And in ParalleX, we treat it as such. There can be multiple processes and multiple threads underneath those. The local control objects, those pentagons, allow you to do very lightweight, localized synchronization. Synchronization using old constructs like the futures construct from Hewitt's actors model, the data flow constructs from Dennis and Arvind and others' data flow models, as well as the more conventional constructs like mutexes and so on. The case of the use of the future gives you tremendous flexibility in the way in which we organize the computation. It allows out-of-order arrival and then synchronization accordingly. It allows you to change between eager consumption of results to be performed and lazy, depending on whether our resources are. The only thing worse than not having enough work to do is having too much work to do. At least in the case of not having enough work to do, the work will go forward. If you have too much, it will get wedged. You will get locked. And so the ParalleX model, through these different kinds of constructs, both for data and control, allow us to have a much more dynamic, a much more flexible model. I would like to show you a couple of these things. I have more slides than I'm prepared to present today, so allow me to jump ahead a little bit. But I want to give you an idea here of what a parcel might look like. It has several fields. Let's talk about 4 fields. A destination. Now, there's another form of work that's been done. It's decades old, called active messages. This work came out of Berkeley, Dave Culler, Kathy Yellick, and others. Of course, it was based on work from the data flow community, and that work, in turn, was based on even previous work. So there's a long tradition of this notion. One of the things that parcels do is it actually allows the work to be applied to specific data in the virtual namespace, carrying an action that tells what kind of effect one wants to achieve. It can be as simple as flipping a bit, or it can be as complicated as executing an entire subroutine. Some argument values may be necessary to go along with the data, and that would be the payload. In the case of data movement, you might want to have a lot of data, many lines, a page or more, if pages are still being used. Finally, one of the subtleties, but extraordinarily powerful one, is the idea of a continuation. The ability not just to move data or even action, but rather the ability to migrate the flow control itself across the machine. In the future, you will not just have a program counter sitting in a thread on a processor. You will actually have a measure of the entire global parallelism that it coordinates the entire machine, and that the flow control itself, that state, may migrate, allowing the work to move to where the data is overall. It's not a new concept, but we have not used it in conventional practices, and it may be time for this opportunity to be exploited. Now, I'm going to jump ahead a little bit here, because I've actually already touched on these points. I find it difficult to push these buttons, and every one of these points has already been made. The question is asked, okay, how do I program this thing? Implicitly, I don't want to program this thing. How do I get somebody else to program this thing? And so I want to address that question, and I will do so by showing you how you should not program this thing. This, unfortunately, is how we're programming it. We call this PXI, and it is the most rudimentary, the most clumsy, awkward way of programming. If you are familiar with MPI, we have benefited from all the worst decisions that MPI has made, and we incorporate the semantics I've already described into conventional languages like C, that's what we're working on, and C++. This gives us very low-level control of the model of computation so that even on conventional machines, we're able to run experiments and evaluate the ideas that I put forth. If you've done a quick scan of the top level, you see things that would be consistent with the idea of managing parcels. In MPI, it's messages. Controlling threads, well, in MPI, that would be their form of processes. Global address spaces, well, MPI doesn't really have that. Local control objects for synchronization, certainly MPI has its version, but these are much nicer, trust me. And of course, the idea of organizing all this computation in ParalleX processes, interfaces to the outside world. So we have a PXI interface, which we've been implementing with, and I'll just jump here, with a runtime system that's experimental called HPX. So everything I've described now is operational, some of them very nicely, some of them would not scale to 100 billion, but they are showing good properties. I have just a couple of additional slides, and I'd like to show you some of these results. Every freshman knows you must all learn how to write the Fibonacci sequence the wrong way. And true to the tradition of computer science, we have done so. But I justify my actions here because we don't want to compute the Fibonacci number. I mean, that's just a result. We're computer scientists. We don't care about results. We just care about doing the computation. If you were writing operating systems, you know another word for bug is user, right? They keep getting in the way. Here is several different implementations of your classic 5-line Fibonacci sequence. The red dots are doing it in Java. Runtime is up, so up is bad, down is good. But it isn't just that the red lines are higher than any other lines. That's not good. Notice it doesn't extend very far. It's not because we got lazy. It's not because my graduate students went off to a football game. And I promised I wasn't going to mention football. I'm sorry. It's just tough not to think. Go Tigers! Sorry. Okay. So instead we did it in P threads. That's the green line, faster than Java. Couldn't take them any further. Linux crashed, died. What are the other two lines? HPX. HPX is able to run hundreds of thousands, even small number of millions of threads, user threads, even on a small machine, and take it out far, much, much further. Also, as we add more cores, in this case we doubled the number of cores, we were able to get roughly twice the time on this. Now, in fairness, we're not the only ones to accomplish this. This is not a unique accomplishment. Friends at MIT running Silk not only have shown and demonstrated the same things, but their numbers are a little bit better than ours. On the other hand, they had a 10-year start, so they're welcome to it. TBB at Intel also. I haven't seen the concert results out of Microsoft, but we can expect the same thing. So this is the use of lightweight threads. The second thing, and the last thing I'd like to show you, is the challenge of trying to achieve scalability where global barriers tend to dissipate parallelism opportunity. If I had a large number of threads executing and they all took the same amount of time, if the first barrier started all the threads and they all went to the second barrier to complete them, well, we'd lose a little bit of time at the strangle point of the barrier, but that wouldn't be terrible. And in fact, that's a very good way to do a lot of computations, and you can't really improve on it significantly. But what if your inner loop is nonlinear, and that the execution time is highly data dependent, and the result is that the total response time of any one loop can vary by more than an order of magnitude. This is, in fact, typical of many problems. The one that we've worked on directly, as I was talking to some colleagues about, is a numerical relativity problem where colleagues like to crash neutron stars together. And it has a wide variance in the length. A bulk synchronous protocol approach means that the second barrier always completes only after the slowest thread. And so the sequential execution only continues at the rate of the slowest thread, although in a follow-on phase, much of that computation might have been able to go forward because the precedent constraints were satisfied by the other threads, which statically are sitting there wasting cycles on those machines. We've run a set of synthetic benchmarks on a fixed workload where the standard deviation of the amount of work on the given thread varies. So the total work never changes, but the ratio of the slowest to the fastest thread does change. As you would expect, as that standard deviation increases, and shown by the red line moving up and to the right, the execution time does take longer. It slows down. But if you're able to overlap the phases dynamically, as you can with local control objects, and as we did with the HPX execution, you find that since the workload is roughly the same, you would expect the execution time to be roughly the same. And indeed, that's precisely what we encounter. Now, these are hardly final or definitive results that I'm showing you. But what they do suggest is that there is opportunity to consider alternative approaches to organizing our computations and designing our machines. And that may, in fact, expose substantial more parallelism and allow us to address the challenges that the new technologies inflict while exploiting the opportunities that they provide. So, in conclusion, I am suggesting that our field of high-performance computing is in a phase change, and in the history of computing, this is the 6th phase change, that the ultra-high-scale computing of the next decade will require, as it always has in the past, a new model of computation to effectively exploit the new technologies and to guide the co-design of those systems. I offer as an example ParalleX as a medium for experimental research that allows us to explore some of the possible ways that such a new model of computation can take on these challenges. And I suggest that some of the early results that we and others exploring this domain are showing very promising opportunity for the next decade of change. Thank you all very much.
We have some time for questions.
Actually, I would like you to address the last bullet. I mean, what sort of applications are you intending with informatic applications?
Thank you for asking this. I didn't have enough time to state this. I'm particularly excited about the graph applications. There are two reasons for this. First, and this is coals to Newcastle, of course, I've been encouraged and enlightened by the work being done here at Indiana University. My colleagues have come here to cooperate and collaborate with these. The graph problems do two things. First, as has been noted by your colleagues here, they are the tougher problems. But they're also ones with greater opportunity. They open up new classes of applications, both in the science computational arena. The specific example would be adaptive mesh refinement, and also some n-body codes that we pursue in molecular biology, but also in the informatics applications. In particular, everything from dealing with national security problems, ontologies for interpretation, user interfaces, and even rudimentary machine intelligence problems. The other reason we're following graph problems is because there is an unused and untapped source of parallelism. That's the parallelism embedded in the metadata that allows a class of computing known as data-directed execution that we simply don't use in conventional methods, and that appear, depending on the problem, to expose orders of magnitude, maybe as little as 1, maybe as many as 3 or 4 orders of magnitude, parallelism that we're not yet using. And so those are the reasons that we're focusing on dynamic directed graph problems. Thank you for the question.
Earlier, I spent 5 years, might have said lost, programming math part MP1s and MP2s. And so immediately, everything looks like a data parallel problem to me. And as you were going through your presentation, that was coming up, and you just mentioned data directed, and I wondered if you could maybe amplify how your approach does relate to that or doesn't.
So at the time of implementation of the mass pars the mass power 1 in particular, but also the mass power 2, along with the connection machine 2, that was roughly at the same time. That they were, for certain problems, providing the best performance to cost and some of the highest performance of any of the machines that were contemporary with them. And they were certainly data parallel machines, but they were synchronous data parallel. The class of problems that we're investigating and the systems that we're looking towards are asynchronous machines, machines that are synchronous within the local physical domain, but enable, support, and manage the asynchrony of operation across the system as a whole, and yet exploit the data parallelism that's embedded within the data structures that global data structures that represent the problems we're talking about.
So in the introduction, you mentioned that you thought this might be the last phase change. Those sound like famous last words.
Yeah,
Potentially
well,
famous.
I'm running out of time, and I want to be famous, and and I'm reminded that people have gotten famous by saying really stupid things. So Thomas Watson said that the world will never need more than 6 computers. Ken Olson, DEC, Digital Equipment Corporation, said that no one will ever want a computer in their home. I once said punch cards are forever, but for some reason the world has forgotten that. So I'm trying again. And so I will state that I believe that there was never a petaflops barrier. There was a petaflops challenge. We had to get there. I believe there is a zetaflops barrier. I believe that using, and here's the caveat, logical gates of any technology, logical gates, we will not get past 128 exaflops. And I think the number is going to be more like 64 exaflops. There's a curve, and there's always some stupid government that will pay too much money for a machine that nobody will, and name it after some flightless bird. I don't know. There'll be some machine called Ostrich. Isn't that cool? There'll be some machine called Ostrich. And so because of the speed of light, because of atomic granularity, and because of Boltzmann's constant, some would say, what about Landauer? Okay, let's throw in Landauer. I believe that the laws of physics simply will preclude, with the current meta paradigm we've been using, the ability to get much past 10 exaflops. And that was my early comment. And I think I will use that as an opportunity to say, again, thank you all very much, and I appreciate your hospitality and my visit here at Indiana University.